Okay, let's have a look at equilibrium constants. And to do that, we might take a simple reaction between carbon monoxide and oxygen to give us carbon dioxide. Now that's a reversible reaction, and at equilibrium, we'd expect to find significant concentrations of both our reactants and our products. We can make some observations about what happens in this system. Let's say that at time zero, we just start with reactants. Well, at time zero, we'd have a high concentration of reactant and very low, in fact zero concentration of carbon dioxide. But over time, our concentration of reactants would decrease and our concentration of product would increase. So at equilibrium, we've already determined that we would have the same reaction going forward as we've got backward. But what would our exact concentration of reactants and products be? Well, to do this, we need to go through a little bit of mathematics. So if we've got a reaction A plus B that's a reversible reaction giving us C plus D, at equilibrium we know that the concentrations of either our reactants or our products are constant. Therefore we can say that the ratio of our reactants, products to reactants, is also constant, which means we can generalize, or we can derive a generalized formula with this constant K. And in this case, and by convention, we put our products over our reactants. So we say that the product of our concentration of our products, C times D, over A times B will always be this constant. Now, more generally, as we saw from our first reaction, we don't have one-to-one molar relationship between all of our reactants and products. So to generalize this equation, we say that the equilibrium constant KEQ is equal to the concentration of our products times the number of moles that we have, the prefix, times the second one, if we have a second one, and similarly we raise to the power of our prefix, all over our reactants raised to their respective powers as well. So let's look at this in terms of our previous reaction. We've got 2 moles of carbon monoxide plus 1 mole of oxygen gas gives us 2 moles of carbon dioxide. So according to this generalized formula above, our equilibrium constant will be our product raised to the power of our prefix. So the concentration of carbon dioxide squared over the multiplication of our 2 reactants raised to their respective powers as well. So we've got carbon monoxide concentration raised to the power of 2 and oxygen concentration raised to the power of 1. Now, do we get the same units for this equilibrium constant every time? No, we don't, and it's determined by these prefixes. So that's why I haven't put any units in here. Now, there's one note to make. Pure solids and liquids are not included in our equation because the concentration of solids and liquids is always constant. So we only use the concentration of our aqueous substances or our gases. So what's the significance of this equilibrium constant? We've got 3 possible scenarios. First of all, if the equilibrium constant is less than 1, if it's somewhere in the range of 1, so I've put here 0.1 to 10, or if it's greater than 10. So in terms of our reactions in forward and reverse, if our equilibrium constant is less than 1, this will favour the reverse reaction. By contrast, if it's somewhere very close to 1, then the forward and reverse reactions will have equal tendency to occur. And if our reaction or our equilibrium constant is greater than 10, then this will favour the forward reaction. So in terms of our reactants and products, if it's less than 1, our reactants are definitely favoured. So the reaction shifts to the left, reactants are favoured. If on the other hand we've got something close to 1, we get roughly equal concentrations of reactants and products. And if it's greater than 1, we get product formation favoured.